Okay, so first of all, I would like to thank the organizer for inviting this talk, from LHC, in this, of course, Holier of theoretical physics, right? So anyway, I will try to give you an impression of the supersymmetric searches at the LHC, and also the search for dark matter candidates, which is also one of the very important tasks that the LHC is trying to fulfill. So first of all, as Massimo already said, so the LHC has resumed, let me tell you some words about the status of the LHC. So the LHC has resumed the operation at 13 TV. The Run 2 is ongoing right now. Since June 3rd, 2015, we have stable collisions, and physics data are being collected by the LHC experiments, including CMS now with the magnetic field on, so this is great. The results that I will present from Run 1 at 7 ATV are practically all final, so this is the heritage of the SUSY and dark matter searches at the LHC for Run 1, mostly. They are mostly published whenever possible. In fact, almost always I will give the references to the results. And so in this talk, I will review in a broad way, because I cannot go in many details. As you see, there are many, many results for SUSY and dark matter searches. And I will give an overview of the expectation for Run 2. So here is just a nice picture of two events taken by CMS and Atlas. There is, of course, the LHC screen saying that the two beams are on, and so everybody is happy, as you can see. Okay, now, what about the status of the standard model after the Higgs discovery? Of course, the Higgs discovery, we've seen this very nice talk from Massimo. It has shown that really we understand a lot even about the Higgs. We can measure it with high precision. Nevertheless, it's a cornerstone, of course, of standard model. So we have completed the standard model. Nevertheless, there are many questions which are open. I don't need to tell this to you, but it's clear that even the standard model asks and demand new physics beyond the standard model. And as Isidore Rabi said about the muon, who ordered that? You can say the same thing about the standard model. Who has ordered this structure of this hierarchy of masses, and so on and so forth. And so the next thing is the status of the universe after Planck. We have seen this very nice talk on Tuesday and by Professor Dunkley. And as you have seen, she has shown that really we understand a lot about the large-scale structure of the universe. And in fact, we even know what the universe is composed of: ordinary matters, 5%, 27% dark matter, and the rest is dark energy, which is, of course, a very mysterious substance which we need to understand. So we can say, at the best, we understand the 5% of the universe. Well, the standard model, with all the questions which are still open, although, of course, now we understand also very well the Higgs, but still, many questions are open. And then the rest is mysterious stuff, which certainly demand new physics, okay? So, is then the next question, as an experimentalist and even as just a physicist, you can ask yourself, is this new physics within reach at the LHC? So as experimentalists, we know that the reach of an accelerator or a collider is depending on the center of mass energy, obvious, because that gives you the possibility to create this particle in the collisions. And then the luminosity, you need enough luminosity, because if the cross-sections are small, of course, you have enough events also to apply cuts and then discriminate from background. Okay, so as we will see in the next plot, we know that the reach of the LHC at 13, 14 TeV is of the order of 4, 5 TeV. So we will explore this scale, this energy scale, or this mass scale at the LHC around 2 and beyond. So is then the new physics which could explain some or all of the questions standard model and beyond the dark matter and maybe even dark, residing in this mass range? Of course, this is a question you cannot answer. I mean, but we have indication, we have seen throughout all many talks which have been given here, we have indication that there is probably something going on in this mass range or is the energy range. So we hope to see something. As you know, supersymmetry provides motivation for new physics at the TeV scale. There are, of course, other models that provide motivation. I will not review it this year. And dark matter provides very strong, I would say, motivation for new particles below and at the TeV scale. So all this is pointing to the fact that maybe something is really going on there. So supersymmetry and dark matter are of course, one of the main objectives of the Run 2 LHC and beyond. Okay, so just to substantiate a little bit what I said before, here there is a plot which you can get from this website. So it's an applet which has been developed by Gavin Salam and Andreas Weiler, and it's a very nice thing, so at least for other experimenters who don't understand much, is it tells you how how going from ATV to 13 TeV, ATV and 20 inverse femtobarn, which is what we collected in Run 1, going to 13 TeV and 100 inverse femtobarn, which is what you hope to collect by the end of Run 2. How much does the mass reach increase? So for example, if you take here 3 TeV, Run 1 goes up to about 5 TeV in terms of mass reach at Run 2. So this gives, of course, the things then depend on the real dynamics and the real details of the theory, but that gives you an idea how much things will increase, how much more you can explore. Okay, so the next question is new physics equal supersymmetry? So of course this we don't know, but if you are a supersymmetry SUSY believer, I think you know that SUSY has very nice features. I mean, of course, was basically invented to stabilize the gauge hierarchy, to provide dark matter candidates, and eventually also to provide the unification of the forces within the standard model, the forces of the standard model, and also gravity. So if you are a SUSY skeptic, and okay, you may certainly be, you must well recognize that supersymmetry, even if maybe is not what we believe or it doesn't exist, is still a very flexible theory that encompasses a large variety of new phenomena. Including the extended Higgs sector, including missing energy signatures, but also, as you will see, long-lived and metastable particles, and really very large set and spectrum of signatures of new physics. So that searching for SUSY, SUSY signatures, whatever is suggested by SUSY, by the many possibilities, many models as SUSY suggests, may reveal other forms of new physics. So even as an experimenter, you say, okay, maybe I don't believe in SUSY, but still this gives me some guidance in looking for new physics. So new physics could emerge from searching for supersymmetry. Okay, this is just the apology of supersymmetry here. So now let's go to the experimental results. Okay, so first of all, let's look at the expected SUSY cross-section for ATV. So there are two things I want to notice here. First of all, that the the gluinos have the largest cross-section, followed by quarks, then by third-generation quarks, and then by the electroweak gauginess, okay? So also you can see that cross-section are said to be high. I mean, often the theories say that SUSY cross-section are high. Yes, they're high. But for example, at 1000 TeV, and so, 1000 GeV are order of 10 to the minus 2, 10 to the minus 2 picobar. So this you can compare, for example, this plot was already shown by Massimo, to the standard model measure cross-section and also to the Higgs cross-section, right? So this is 30 picobar, okay? So we are comparing, so we just put things in a framework. This cross-section, SUSY cross-section are high, but in the end they are not so high, so there is, they need a lot of luminosity, they need a lot of, and they are competing with this kind of backgrounds, okay? So there is a need for quite an amount of luminosity also to do SUSY searches. Okay, so just to give you an overview of the searches that have been done at Run 1. So both Atlas and CMS have searched for Gluino and first and second generation quarks. So third generation quarks, stop as bottom, electroweak gauginous, and other SUSY beyond the MSSM. So with a particle violation, long-lived particle searches, and beyond MSSM signature, in a large variety of final state and many different techniques, which I'll try to give you a flavor of because it's really huge amount of searches that have been taken place. Okay, so this is just a synoptic table of the numbers of actually these are all papers which are now being published related to the SUSY search at LHC in Run 1. This is by Atlas, and the same thing is by CMS. So there are, I've given the slides so you can look at this at the references. Also, the references are found in the web pages of the experiments. So you can just have an idea that there are really a huge amount of work done and a lot of varied searches, okay? So okay, so to continue this discussion, what we can say is that supersymmetry can manifest itself in, broadly speaking, in two classes of events with high missing energy, missing transverse energy, which is somewhat a canonical way of looking for supersymmetry due to the fact that there are, in the cascade decays, in the end, there are particles, invisible particles in neutralino typically, or others that don't, that are not detected, so they leave transverse missing energy in the in the event. And then there are signatures beyond the MSSM, for example, which are without missing energy, okay? But they are still within some SUSY framework, which I will try to give you a flavor of. So I will now say something about the experimental searches, I mean, how searches are done, and then go on and show mainly results because I don't have a whole lot of time. So first of all, missing energy, okay? So as you can see here in this plot from Atlas, okay, that's a search for gluinos in Atlas in a very recent paper that shows the missing energy, how it's measured, okay, for background, for standard model processes. You can see over different order magnitudes and the region where you expect the SUSY to show up, so high missing energy. So the trick here is to have a very high control, very good control of the missing energy tails, of course, which both the experiment, Atlas and CMS have, and you can see this through the fact that there is a very good agreement throughout different order of magnitudes in the missing energy variable. So that's one of the typical searches that you can do. Just you do a selection of events, and then you apply a missing energy cuts, and typically you can get sensitivity, for example, to the most abundantly produced SUSY particles that are gluinos. Another variable which is a bit more complex, but not so much after all, because you can write it into formula, is the Razor variable, which is a variable that takes into account the topology of these events. There are typically two heavy particles decaying and producing, among other things, missing transverse energy. So what you try to do is to try to use the full event information as much as you can of the kinematic variables that you measure in the event. So the momenta, or the moment of the jet, or all the physics objects are reconstructed into two, let's say, mega jets. So you have an event which is kind of summed up into big jets, for which you have you have all the kinematic variables. So you can reconstruct this mass, I mean the mass of the object, and the presumed mass of the object and transverse mass of the object. And you can form this R variable, which is the ratio of the two, and then you can plot R squared versus M versus this mass, Razor mass. And you can see that for the standard model, the data are sort of accumulating in this corner, while for supersymmetry particles, here is the gaugino of 1300 GeV, the signal is more much displaced. So this is one of those variables which helps you to discriminate effectively in the supersymmetry searches. So the search, first of all, the search for strong SUSY production. So this includes various cascade decays that I don't list here. So this is from this paper from CMS. And so I try to show you now some results. These are all the most recent results, and everywhere you can find the references. So this is a combination of several, in fact, many searches, as you can see here. Overall, what it is the interpretation of the SUSY, Gluino, and Quarks searches in the framework of so-called constraint SUSY model, CMSSM, and MSUGRA. And this is the mass M0, it's M1 alpha versus M0, the mass, so-called universal gaugino and universal squark mass, in which, I mean, within this model, one represents the results, but they can be translated also in limits on the physical particle mass. So here, for example, you can derive from this plot a Gluino, a squark mass limit of 1.6 TeV about, and the Gluino mass of 1.4 TeV. So these are strong limits, but they are within the constrained MSSM framework. So yes. The CMS, so this was Atlas and CMS do similar things. So CMS has also another approach, which is, so they do the same search as Atlas, but the interpretation is done also in so-called simplified models. So these simplified models, you don't take into account all the relations between masses and branching ratios calculated according to the parameters of the model, which typically are many, which you can reduce like constraint model, but they're still many. So what you do instead, you try to select masses and branching ratio which are justified from what we know, for example, from naturalness, but they are not related specifically to a model. So it's a little bit, they say, more model independent. It's not really more model independent. It's just that you use a different approach. You use some specific mass hierarchy and so on. And anyway, at the end of the day, you can derive these kind of plots. So you measure cross-section limits for cross-section of time Lorentz ratio limit for each mass combination, and you can, within certain assumptions of the model, you can derive this kind of excluded regions, okay? So these are, as you can see, limits are a bit lower, softer than in the case of constraint models, okay? But they're still quite significantly in the 1 TeV region. For neutralino masses that go from 200 to 400 GeV, practically, you have almost closed the region. But then as you go up in neutralino masses, these limits soften up, okay? So, okay, that gives an idea that, okay, there are still regions that, of course, need to be explored, and they are left unexplored by the LHC Run 1. So, so now, what did we get from LHC Run 1? That there is that it seems that first and second generation fermions, quarks in particular, appear to be heavy. Otherwise, we would have seen them. We didn't see them. So is this excluding supersymmetry? I think we cannot say that yet. And in fact, theorists have come up after these results, negative results, have come up with the idea of a natural supersymmetry, which says, okay, the quark can be heavy, so that's why you didn't see them, because maybe they are even beyond the reach of the LHC at ATV or so. But the third generation quarks like Stop and Smotom can be lighter. And remind you that the stop, of course, plays a very important role in the stabilization of the mass. It's one of the, the reason also for having supersymmetry eventually. And so what you get is a spectrum where the quarks are large, but the Stop and Smotom are relatively light, as well as the Xeno, okay? Now, the Stop and Smotom line is a good news. The Xeno is a little bit less good news because it's very difficult to see at the LHC. And, okay, it appears that this seems to be not a very good dark matter candidate. But, okay, I mean, this is one model, okay? This is one model well motivated that people have explored, but, okay, maybe other models are possible too, and other dark matter candidates are possible, as you will see. So I go on the stop search. Okay, so the stop decays typically into if the mass is big enough, into top, and okay, top and decays according to standard model branching ratio and a neutralino. So in all cases you have two top and the missing energy, and in where the top decay, the decay in a real top is not allowed, you have decay in a virtual top and even a decay in a C plus than neutralino. So these are somewhat different regions, different kinematic regions that requires dedicated searches, okay? And I show here the results from CMS. Okay, so here you can see that there are different dedicated searches that have been put in place. Okay, they have a certain reach for mass of the stop up to 700 something GeV. For masses of the neutralino up to, let's say the region is closed for mass of the neutralino up to 200 GeV, and above 200 GeV, when the neutralino becomes heavier, of course, this exclusion dies a little bit up. Also, you can see here the mass, the exclusion for in this kinematic region where the stop cannot go in a real top, and here where the stop goes into a C quark and missing energy. So these are all dedicated searches, but you see that there are clearly holes opening up in these regions, holes that are not covered by present searches. So this one shouldn't take it lightly, and in fact people take it very seriously. And they do, so here is the same, is the same plot for Atlas, okay? And so you can see the same, a little bit, the same features, uncovered regions. And the people take very seriously, and in fact, they try to do dedicated search. For example, this is a search for four-body stop decays, okay? So where the graph, the process that you're looking for is this one. So you look for low energy, so you require an ISR jet, so to tag the event, and soft leptons and jets, plus missing energy, okay? And this, this search is supposed to cover up this band, this kinematic band, which is not covered by the conventional searches. And as you can see, indeed, there is quite some sensitivity in the search. So this is one of the examples of doing alternative search to cover up the holes or the gaps in the parameter space. Another search is, this is actually a precision measurement, which then is interpreted as a search, is in the region where the stop mass is very close to the top mass, which we have seen is not covered by conventional searches. So what you can do is to measure the spin correlation in TT bar events. And in the case of the stop, the spin correlation are expected to be different from the standard top. And from the difference, you can sort of set, either you see a signal, so you see a deviation from the expected spin correlation in the standard model for top events, or else, if you don't see a signal within the uncertainty, you can set a limit on the contribution of stop events to your sample. And this allows, this allows to put a limit on the stop, on a light stop up to 191 GeV. So these are ideas to say we are trying to cover all possible holes. Okay, so now I go to another search. So SBOTOM is also a third generation quark. Okay, so here is, this is the kind of process we are trying to look at. So event with jets, leptons, and missing energy. So the leptons are the key here. One tries to measure, after a certain number of cuts, a certain selection, which includes leptons and missing energy, one measures the invariant mass of the two leptons. So these are same flavor, E, mu, mu, opposite sign leptons, okay? And what you expect to see in this kind of, this process, cascade decay process, is a spectrum which is a broad distribution with an edge. In fact, it is also called the edge search, okay? So basically what you expect to see if there is a signal is a little bit of an excess in this region, in the low mass region, okay? So, this is, I think, CMS has done the search. So what they see, in fact, is very good agreement in all control region, control sample, except that at the end of the day, when they do the mass plot, there is a 2.6, we call for the moment, upward fluctuation in this mass region between 20 and 70 GeV. Okay, a similar analysis is done for another topology, also for SBOTOM search. And again, also, here you expect a little bit of, a little bit of an excess in the low mass regions. And there, in fact, you see like a 2.4 sigma excess. So these are very small excesses. Nobody's claiming anything, but there are probably things one should watch for. So the next thing you do is to ask your sister or brother experiment to look in the same region, which is when you see some kind of an excess, which is exactly what Atlas has done. So they've done a similar, they've done, they were doing a search for Gluinos, okay, which has a similar final state. So they also look for jets, for soft jets, leptons, and missing energy. So they've done the plot for a very similar selection. So here is the signal that we are looking for, the edge signal I was talking about. It's very nice pictured in this plot. So, and the net result is I don't see no effect, no excess. So, okay, we stay with this. But on the other hand, they've done another search in the Dilepton channel, okay, also for gluinos with the gravitinos at the end, also a massless particle that carries the missing energy. And so they select events with on-shell Z, okay? So the plasma reconstructed is coming from the decay of a Z. And so after the, after full event selections, basically what you expect is from standard model is these distributions here. And this is what you expect from the signal, and these are the data, okay? So this is an effect at the 3 sigma level, and it's published, so it's in the public domain. But vice versa, CMS does not see this excess yet. So anyway, this is interesting stuff we can look at. Okay, then I go on the Electroweak SUSY production. So why is it important to look for for electroweak gauginess? Because as within these natural models, they could be light, so we certainly need to look at that. You can see that there have been a lot of searches being done, and I show you now the results. Okay, so these are the latest exclusion region in the for leptons and neutralinos. So there are you can see that masses are excluded up to order of 700 GeV, depending on what assumptions you do. Okay, you have as usual the regions, kinematic region close to the kinematic limit that are not covered. So these are taken seriously. People are trying to cover them up. So we have to look really everywhere. But for the moment, that's the results we have. With the new data, we will certainly do more. Okay, and then I go here a little bit quick on the SUSY beyond the MSSM, which induces no missing transverse energy signatures. So these are, very large number of models, MSB, GMSB, split supersymmetry, and other models are partly violation. So you can have heavy charged particles that may decay in the detector or may go through the detector, so leave tracks, which are even stopping tracks or just starting at some point in the detector. I will show these in a moment. Okay, so you see this in this plot. So there are all kinds of possible signature, displaced jets, lepton jets, displaced leptons, and so on, with the signatures of tracks stopping or starting at some point in the detector, depending, of course, on what kind of signature you're looking at. And so these kind of particles are actually, there is a large program of research at the LHC to look for this kind of particle, because they could indeed give a signal of supersymmetry, maybe non-conventional supersymmetry, but still. And so this is a synoptic view of the results of the search for these long-living particles from Atlas. So what is excluded is the region below the curves. Okay, so this is this is the mass limit as function of the lifetime of the particles. So you can see that, okay, limits up to 1.5 TeV are even, 1.5 TeV are given, but of course they depend on the lifetime of the particles, so they go down to even like 400 GeV also. So here also there is still room for improvement and for searches. Okay, another search beyond the MSSM that has been done because this model was relatively recently coming out. So it's Stealth SUSY. Okay, what does it give? This is not picked up by standard or conventional missing energy searches because it gives very little missing energy. And so you look in general for relatively soft jets, but a lot of them, so that's the idea. Soft jets is difficult, but since you have a lot of them, you can of course use them for discriminating from standard model. So this is in fact what you have is this ST variable, which is the sum of all the objects in the events. If you have an event with a lot of objects, of course the ST, which is the case in Supersymmetry, is you expect the ST variable to be large. Okay, and here you see a signal, while for standard model in general peaks at very low values. And these are, okay, the excluded regions from the data. So again, up to about 1 TeV mass of the quark is set. And this, okay, depends as usual on the detailed parameters of the model. Okay, so finally, this is the grand summary for Atlas. Here there are all the references and the limits. So limits in the 1 TeV range, of course, are as I've shown you, are given, but also there are much lower limits and there are uncovered regions that need to be covered. And the same thing for CMS. Okay, so now I go on to the searches for dark matter. So this is, probably you all know this. I mean, we are not in competition with the experiment to look for dark matter, for the cosmic dark matter. What you are trying to do is to eventually create the dark matter candidate particles in the collision and then analyze the blob here, what happens. What is the interaction between the standard model particles, what we have in the collision, the LHC, and the dark matter. Of course, once you can analyze, if we could analyze that, this would be very beneficial also for all the other experiments which are looking for detecting directly or indirectly dark matter in the cosmos. Okay, so this said, what do we do? So first of all, let me show this plot. What kind of particles, dark matter particles, are we looking for? This is the dark matter particles in here. So the WIMP and, of course, the neutralino, so SUSY, the SUSY-like dark matter particle. There are a lot of other possibilities, some of which have also been discussed previously in this symposium, but that's okay, that's what we focus on at the LHC for now. Okay, so how do we look for dark matter candidates at the LHC? So dark matter, by definition, is a weakly interacting massive particle that leave missing energy. They are not visible. So how do we get them? Is by tagging. So they are producing these kind of processes, and they just produce nothing, so you wouldn't see nothing in the detector. What you do is to try to tag a initial state radiation gluon, okay? So you say there is initial state radiation gluon, so there is a collision happen, and then there is lots of missing energy. And typically what you do is to look for, so monojets, monophotons, monotop, mono everything, okay? Single objects, okay? The other thing was already discussed by Massimo, so is the Higgs portal model, so which, where you create the Higgs, and the Higgs can decay into WIMPs, into dark matter particle candidates. And so again, there are possibilities to see this, but this I will go faster because Massimo has already reviewed this. And then there are so-called two or dijet, in fact it's more than dijet, it's CT bar and BB bar final states, okay, that are also looked at. Okay, so 2 words on interpretations, because as I said, we don't know what is the interaction between the standard model particle and the dark matter. So there are 2, let's say for the moment, okay, there are 2, let's say, two approaches. One is used at the LHC for interpretation of the data. One is so-called effective field theory, okay? So where you don't make any assumption of what goes on in this blob. Typically, even if there is a messenger particle or a mediator particle, it's very high mass, so you can sort of neglect its detailed interaction in calculating cross-section and branching ratios. So you just make assumption on some potential that takes on in the interaction, okay? So there is, in other words, here there is no mediator mass involved. In the other case, you can assume that instead that there is a mediator mass, could, for example, even be a Z prime or other heavy mass, that this somewhat could be created, or even if it's not created, is virtually, in the interaction. And here you have models that, of course, have a dependency on the mass of the mediator, okay? So they give slightly, in fact, sometimes more than slightly different results. So even here, there are a lot of published results. I put all the references that you can see in the slides. So you can see that all kinds of searches that I mentioned are covered. And others, yes. So many searches have been covered. So I show here very, very small selection of these searches. So one is the monojet search that I discussed. I discussed before. So here the key is, of course, missing energy. Again, missing energy spectrum measured, missing energy distribution measured by CMS, very good control up to very high transverse energy. So, and these are the kind of plots and result and interpretation that you can get from this search. So the monojet is one of the most sensitive, and that's also why I show it. So anyway, you can see here is the upper limit on the cross-section of the dark matter with the standard model particle interaction set by CMS, okay, and compared to limits by direct search experiments, okay. So you can see that they are quite comparable. The limits from LHC are quite comparable, and actually, as already was shown for the Higgs portal models, they kind of cover up the low mass region. Okay, so this is interesting. Of course, it has to be verified if we are really comparing the right things. But okay, there is certainly interest in doing this kind of plots. So this is for two types of assumptions, so spin independent and spin dependent. Okay, and there are various other assumptions on the type of interaction which are consistent with what used by the direct search experiment. Okay, so here I want to show this because I think it's interesting. So this is the other approach using simplified model with the mediator particle. Could be a Z prime, could be other things. I had the plot with the Z prime, so I put the plot with the Z prime, but could be any other particle. And so here you have limits. So always from the experimental results that I've shown before, you can set limits on the coupling as function of the mediator mass. And what is excluded is the region under the curves. Okay, yes. So here the invisible, go very fast, invisible Higgs search was already reviewed by Massimo. So again, this feature that the LHC searches can cover down to low mass. So if this is confirmed, I think it has an impact also on the direct searches. And finally, so the LHC prospect. So this just show here is the LHC long-term plan from 2015 2035 for the next 20 years. So there are, you can see the different long shutdown, okay? So we are here now in 2015, okay? The run will go on for 3 years. About 100 femtobarn are expected to be collected. Then for the next run, where also the energy should be up to 14 TeV, from 13 to 14 TeV, there should be collected 300 femtobarn. And finally, at the high Lumi LHC, there will be 3,000 femtobarn collected. Okay, so I give predictions just for the next run. Okay, there are a lot of papers on also prediction at the high Lumi LHC. Anyway, for the next run, this is the Gluino early run 2 discovery. So this is just up to 10 inverse femtobarn, so it will be very, very soon. So, and this show the significance, okay, the significance as function of the mass of the Gluino. So what you can see is that, okay, for certain masses which are not excluded already with 10 inverse femtobarn, you will have sigma at the 4 sigma level. So if CMS has also 4 sigma, this is clearly already quite a discovery. And then, of course, you can accumulate more luminosity, as we have seen, 100 inverse femtobarn, and much more significant signal can be detected. So this is a larger view, okay? So this is a mass reach of SUSY searches in run 2 and high luminosity. So shown here in light blue is run 2, and the high luminosity is the dark blue. So you can see that you can explore up to certainly the 2.5 TeV mass scale with already a run with the yes, okay, already with run 3 and for sure with the high luminosity. Okay, so I go to the conclusion, to the summary rather. So the CMS and Dallas collaboration, as you have seen, are covering a vast spectrum of possible SUSY and dark matter signatures. So far, there is no significant deviation from the standard model observed. So there are a few upward fluctuation in the 2-3 sigma effect in Dilepton mass edge searches, which I have described with, so they certainly are worth watching, continue to watch what happens with the next data. So I've shown that to you that stringent limits on many SUSY scenarios and dark matter candidates have been set. But what is probably more important is that there are lots of holes, lots of gaps in the searches we are doing, and we are doing a great effort to fill up and to look also in the regions where the search is more difficult. I've shown you some example for the stop. Okay, so indeed there is also need maybe for new techniques, and some of them are being developed, are called, for example, understanding reconstructing particles, reconstructing the top, reconstructing a W, reconstructing a Z, rather than looking for leptons and say jet in the traditional way. So in this has been shown that can be done, and that's will certainly bring new power to the search. So on June 3rd, 2015, the LHC has restart collision 13 TeV, and the run 2 LHC run 2 is ongoing. So with the increased energy and luminosity of run 2, Gluinos up to about 2 TeV are within reach. Many other discoveries are possible, I mean, as you have probably seen. But of course, okay, if nature is graceful to us and gives us a new physics in this mass range. So after the Higgs discovery, which is of course a great thing and a great progress, we have a great responsibility to use, I mean, the detector and the machine, the LHC machine, which works really fantastically well, to really cover up not to miss anything, to cover up every single piece of parameter space or model that is up there, and to make sure that we are not missing anything. So if there is new physics, we really have the responsibility to find it. And just to finish with the cartoon, so okay, this is a responsibility, I would say, for the whole help community. So everybody can help, theorists, experimentalists. So indeed, you can help to leave no stone unturned. How? By, for example, developing models and also methods, analytical methods that can make the search really bulletproof. So we are sure not to miss anything. If there is something, we will find. Thank you very much.
Thank you very much. I think we have time for a few questions. Gustavo?
So, speaking of not leaving any stone unturned, so in the long-lived searches, you showed that you have several ways. You have disappearing charge tracks, appearing tracks, but what about charge tracks that then will decay to, say, jets? Are those events sus-vetoed or
No, there are searches for displaced jets. I mean, there are. I mean, I don't know if that's
charge
yes,
tracks then decay.
Yes. I couldn't. I mean, also in the plot that I've shown, there is a region which is covered by this specific search. I mean.
Right. Thank you.
Other questions?
This excess on the Z peak of the dilepton, how fast could it be clarified, or that it's not there, or that something is there in this neuron?
So if you assume it's a signal, you sort of evaluate a cross-section of this. I mean, within the next, say, 30 inverse femtobarn, it could be either it shows up to the 5 sigma, so then also Atlas. I mean, as you've seen, the CMS sees something that Atlas doesn't see, and vice versa. So then also the other experiments should see it. If not, it will be, I mean, it will go away. I mean, for the moment, it's not called signal, it's just fluctuation. So within the run 2 will certainly be settled.
Okay, so we had a very lively session. So we thank the speaker again, all the speakers, yeah.